I will start thanking the organizers, Elisa and Joan, to giving me the opportunity to present their paper on this symposium. There was, nothing had to do that they were causing the paper to be selected, I hope. So, as I said, I will be presenting this six-hand paper, and we are going to develop a gravity model for cross-border electricity trade. So, from a point of view of a trade economist, when we think about economic integration, if we Google up economic integration, we will get all kinds of words like productivity, monetary policy, and basically this sums up to one thing, which is euro value, no? Trade flows. Trade economists are obsessed with extensive margins, intensive margins, euros. But we normally don't think about a silent integration that has been going throughout Europe, which is an electricity integration. No? This has remained, let's say, relatively silent to trade economists. On the other hand, when energy economists talk about energy integration, they build up all this Nord Pool, Nibel. They start thinking about all the different market coupling mechanisms that have been built up through Europe. But energy economists, well, here you can see the spatial distribution of this energy integration. But normally energy economists miss, let's say, the trading part of this energy integration. These are the different coupling mechanisms and all the trade flows that are going, all the electricity trade flows that are going throughout Europe. No? So the aim of this paper is to bring these two worlds together, to bring, let's say, the trade economists and energy economists together. So, coming from a different field, what I was asking my colleagues, which are much more knowledgeable than I am in energy economics, maybe I can ask the audience. So, if I was to sum up all the value of electricity which is consumed in 1 year, how big will I be? Will I be bigger than the United States? Will I be bigger than Russia? Will I be bigger than Germany? What do we think we are? I mean, are we studying an important market? Where do you think that we will be? If I was going to add all the euros spent in electricity in 1 year, this is the GDP, this is the countries organized by GDP. Where do you think? Guess? Number 1, 2, 3, 4? No guess? So I will be as big as Japan. So in my point of view, we are studying like an economy the size of Japan. So if I was to be a country, it will be a relatively bright and big country. No? This is just to introduce, I mean, most of you work in energy. For those of you who don't work in energy, we are speaking about a relatively important issue here. No? So this is the outline of my talk. And I'm going to give you, let's say, in the next picture. Well, this is what we do in the paper. We develop a gravity model for electricity trade, and we estimate it. No? So we are going to bring some analytics, some modeling, and we are going to build some econometrics. But here is the main result of the paper. This is gravity. This is gravity going in electricity trade, which is certainly something astonishing. No? We have the distance. All the points here represent country pairs, and we have the energy flows. So as you can see, country pairs that are distant tend to trade less. Why? Why would that happen? I mean, if we think it from a trading point of view, I mean, distance represents a transaction cost, a distance cost. I mean, it's more expensive to ship a container ship between Spain and the US that send a truck with Spain and France. So this is, let's say, something complicated kept short. So how can you escape gravity? You can escape gravity by 2 means. The first one is by the country size, GDPs. So countries which are bigger can escape this, let's say, gravity push. So here we represent all the country pairs which are on our sample, and the size of the bubble represents the joint economic size. So you can see that there are some countries here, there are some less countries here, but there are some countries which can escape this gravity push. Okay? So what's the second means that country pairs have to escape this gravity? It's economic integration, it's institutional agreements, it's market coupling. So you can contest gravity by being big or by being smart, let's say. And here in red, we represent all the country pairs in Europe on our sample that have some kind of market integration mechanisms. And you can see that it's also, there are some countries here which will come to the residuals, but there are some countries which are above, let's say, the ideal regression line, who are able to escape this gravity push, who are able to hedge the transaction cost related to interchanging mechanisms by being smart, by having some kind of economic integration, by having some kind of market coupling. So this is basically the idea, the intuition behind the model, and we will bring some analytics to this figure, and we will estimate what is the effect, what from those two hedging mechanisms, which one represents like the bigger hedge, the bigger gravity escape. Okay? So we have to think that we have to introduce in our model some kind of capacity constraints. I mean, I would want to trade with one country, but if I don't have enough capacity within the pipe, I won't be able to do that. No? So we have to bring some capacity constraint trading to the model in order to be, let's say, a relevant analytically model. Okay. So previous work. I mean, we are not the first ones to investigate which are the energy integration mechanisms to produce, let's say, real-world outcomes. I will speak about in detail of one of the papers in detail, which is this one, which is a previous work of us. This is a little bit publicity. If you're interested, you can read it in the next issue of the Energy Journal. So basically, in this paper, we delivered the first gravity equation. It was developed in a film level setup, in a Melitz kind of setup, but we didn't use it. We just needed this equation was just a byproduct to investigate what was the effect on a real world outcome, like FDI, of a market integration mechanism. So, based on that work that we did previously, what we do is we go to, let's say, Gravity 101. We get an off-the-shelf model, Anderson and Van Winkop, 2003, and we adapt it to our, instead of trading goods, we adapt this model to trade electricity between country pairs. So, I mean, there is a special allocator between the importer and exporter, there are constant elasticity or substitution, and there is market clearance. So there are, let's say, the three kind of setup that, let's say, seminal paper like Alkolakis and co-authors in 2004 will say that whenever you have these three setups, let's say a gravity equation will pop up naturally. So you have to think that there is an electricity pie. No? There is a big electricity pie in the world, and a pair of countries will slice that electricity pie and get different parts of the pie, depending on what? Depending on how big they are. This is those were the big bubbles. However, there will be some constraints to the amount of pie that you can get. I mean, ideally you would want a big slice of pie, but there are some things that will limit the amount of pie that you are going to get. So basically those are the prices that you observe from the importer, the prices that you observe at home, transaction cost, distance, and we will introduce here this kind of capacity constraint, which will be modeled by institutional agreements. No? So basically, you want to think about the trade between country pairs as if there was a frictionless trade. This is the amount of pie that you wanted to get if we were in an ideal world where everybody had the same price, and you will be only constrained by how much energy you were able to produce and consume. And here you will have trade frictions, which will be based on what we said, distance, capacity, institutional agreements, and prices, your home price, the price from the exporter, and also you have to think that there will be some kind of multilateral resistance to trade based that you can also source energy for third countries. Like, for example, Germany can source energy from Austria, but it also can source energy from another important country, for example, like France. So you have to take into account third country effects in the gravity equation. Okay, so this is, let's say, taking this seminal knowledge of multilateral resistance in trade literature into energy trade. Okay? So the predictions of our model are basically for this, like, let's say, economic differentials will affect bilateral trade, and there will be also some kind of modeled by some institutional and physical constraints, and we would like to see that electricity flow trade will increase with the installed capacity, and there will be some kind of third country mechanisms that we have to account for. Okay? So now let's take our analytical setup into a tractable equation. So basically we will have this kind of setup. No? We will have the log of bilateral energy flows, pairs of countries in time. We will see what is the effect of the GDP of the importer, the GDP of the exporter, the distance, some kind of, let's say, cultural mechanisms that might affect this relationship. For example, if the countries were part of a colony, if the countries had a common language, this just makes things easier to manage, let's say, in a kind of trade setup. And here we have our variable of interest, which is if there is in a certain year an agreement or not between country pairs. Let's say a market coupling mechanism, which was this table that I presented in the first or second slide, which energy economists, let's say, like a lot. And we will also control for country fixed effects and time effects that will account for these third country mechanisms. We will turn to a PPML estimation, which takes care of heteroscedasticity at the errors, and also will take care if there are two countries which didn't have a positive energy flow in 1 year in particular. So we can adopt an estimation procedure which is compatible with zeros and which is, let's say, the norm in this kind of gravity models. Okay, so basically it's just taking the exponent of both sides of the equation, and then we will have, let's say, a nonlinear estimation, but the interpretation of the coefficients is very similar as if we had a natural double log specification. Okay, so let's go to the data. I mean, Europe is not as kind as Singapore, as we read in the data, but okay, we have what we have. And we collected data for 38 European countries. So you have to think the amount of different country pairs that we have in our setup between 2003 and 2013. This is recorded in gigawatts per hour, and we took the gravity controls from, let's say, a standard gravity setup provided by the French institution CEPI, and we got also electricity prices per country for Eurostat, and we averaged them for a year. So these are the results. And turning, let's say, to the first column, which is the very relaxed specification, where we don't account for these third country effects, but we can see here that the GDP of the exporter is significant and positive, the GDP of the importer is significant and positive, and distance is negative and positive. So basically this is gravity. This is the graph that we saw. Distance has a negative effect on energy trade flows, and this can be hedged by being a big country, being a country which has a lot of, let's say, energy being produced and consumed. We can see also that, for example, being landlocked or having a common language is also a positive thing to which increases trade flows. Basically, if you are Switzerland, you will tend to import more electricity for neighboring countries than if you are the United Kingdom. Why? Because you are close to other countries which might build a cable to your side. So here we are introducing different sets of controls. For example, here we introduce country pair fixed effects. Then all those constant country pair characteristics like distance, landlocked, will be absorbed by these effects. And we can see that here what surfaces, it's that we are the importing mechanisms. No? So basically what we can see in this column is that it's not really the GDP from the exporter, it's the GDP from the importer. No? If I have a big demand for electricity, basically, if my economy is booming, I will have also a big demand to interconnect, to import energy from other countries. When we put the prices of the exporter and the prices of the importer, we can see that we have also, let's say, mechanisms which are compatible with economic intuition. No? If the price of the exporter goes down, that will increase electricity imports. If the price of our exporters goes down, that will decrease energy imports. So these mechanisms, let's say, are compatible with what we will expect. However, these mechanisms are not significant if we introduce country fixed effects, which will take into account, which will absorb all the price mechanisms at the country level. No? So this is also something that we would expect from a model. So here we turn to what's important. What's more important? Size or smart? Being big or being smart? So we can see that both are equally important. For example, the GDP of the importer is still positive and significant, and when we introduce a dummy variable which takes into account all the different energy integration mechanisms that have been going throughout Europe, we can see that this effect is positive and significant. So being smart is positive to increase your electricity flows. We can see also one thing which is particularly important, that we observed also a diversion mechanism. This diversion mechanism means that when I have two pairs of countries which are equal in economic terms, I will tend to import more energy from that country which, all other things considered, has signed an agreement with me. So we observed that there is a positive incentive to join this kind of integration mechanisms, because otherwise I will lose electricity trade. So this is, let's say, the notion of trade diversion in trade economics. So we observe this kind of electricity diversion when countries which are similar to other countries, which would have trade otherwise, end up losing electricity trade just because they are not smart, basically, no? And here we see that this persists if we control for country paired fixed effects, which would be the most robust specification. Okay? And here we turn to the detail. There is a big heterogeneity in this variable which controls for all the different electricity integration agreements. And we can see that there are three agreements with servers which have, let's say, the bigger impact, which are driving these electricity integration mechanisms, which are basically Nord Pool. We can see that in all of them we see this diversion. No? Basically, it's the Nord Pool, the Northwest Europe, and the Northwest Euros plus MIBEL plus Spain and Portugal, which are the main drivers of this impact that we've seen. Okay, just to finish my presentation. So I think you were convinced by this presentation that we have this energy, this gravity push between trade partners, between electricity trade partners, and we can contest that pull either by being big, by being smart, or by being both. Okay. So in the pipeline, so our future intentions to finish up this paper would be to introduce specifically in the model network capacity. We have not been able to do so. We are working on the data. It's not that easy to do the data. Maybe if we were to do this in Singapore, we could get the network capacity data. But here in Europe, it's a little bit more complicated. We have to go country by country. So if there is any kind of regulator here who is willing us to give us the data, we will be charmed by your generosity. And also we were interested on this discretionary price cap and interconnection outages, which might somewhere affect this mechanism. No? So for example, there was this big outage in France. No? So there was Spain was the only one providing energy to France because they wanted to build the interconnection, but other countries which neighbored France just shut off the interconnection. So this kind of discretionary mechanism should surface in our estimations as well. Okay, so thank you.